Imagine AI knowing you, not just from your browsing history, right? But from something far more mundane, almost
Ooh.
intimate, your trash.
Yeah, it sounds a bit like science fiction, doesn't it?
It really does.
Mhm.
But this isn't just a concept anymore. It's actually happening. AI is already sensing, classifying, understanding complex patterns in practically everything, right down to what we throw away.
Mm-hmm.
So what is a pattern to an AI, really? And what does this capability mean for our future?
That's the core question.
Today, we're doing a deep dive into a fascinating report, AI pattern recognition in human waste management. And, this isn't just about better recycling.
Not at all.
It's really a profound case study, I think, in how AI's fundamental ability to find patterns is transforming these complex real-world systems. And what that tells us about AI's potential to understand, well, maybe everything.
That's right. And our goal for you listening in is to get a really clear grasp of the mechanics here. How does a machine actually see and learn from data? We'll walk you through this powerful, tangible case study, waste management, showing it in action. And then, crucially, we'll dig into the philosophical side. What does it mean when AI becomes this universal tool for explaining existence itself?
So a shortcut to getting really informed on this.
Exactly. Your fast track.
Okay, so let's unpack this. When we talk about AI pattern recognition, what are we really getting at? It's about simulating human intelligence, basically.
Essentially, yes. But the key part is machine learning, which lets systems learn from data without needing every single step programmed explicitly.
Right.
And pattern recognition is a huge piece of that puzzle. It's where the machine identifies, interprets, and then, importantly, acts on recurring structures it finds in data.
So for an AI, a pattern isn't like a picture it sees like we do.
No, not quite. Think of it more as a consistent characteristic or a regularity in the data, something that lets the AI classify a new thing or make a prediction. These patterns can be visual, sure, but also auditory, textual, numerical, really any kind of data. And the sort of magic happens when these patterns get translated into something the computer can actually process. These abstract mathematical representations, often called feature vectors.
Feature vectors. Right.
Yeah, it's like mapping a really complex idea onto a specific point in like a high-dimensional space. So a handwritten 7, for example, might become a vector listing pixel intensities.
Okay.
Or a human face, for facial recognition, could become a vector of geometric measurements between key points, landmarks on the face.
That translation from raw stuff to this abstract feature vector, that's really interesting. Can you walk us through the actual pipeline? How do we get from messy, raw data to something actionable?
Absolutely. It always starts with data acquisition and preprocessing. You absolutely need good data, high quality, diverse, relevant data.
The foundation.
The foundation, exactly. But raw data is almost never perfect. So it gets cleaned up, noise is filtered out, values might be normalized. Sometimes data sets are even augmented, expanded artificially to make the final model more robust. Next up is feature extraction and engineering. This is where the system identifies and pulls out the most distinctive attributes, the really important features from that cleaned up data.
Like the edges in an image.
Precisely. Edges, corners for images, maybe specific frequency components for audio. The goal is to reduce the complexity of the raw data into that more manageable, more informative feature vector we talked about.
Right. Distilling it down.
Exactly. Then we get to the core learning part, pattern detection and model training. Now, if your data comes with labels already, like pictures tagged cat or dog, that's supervised learning.
Okay.
The model learns to map the features it extracted to those correct labels, so it can then categorize new, unseen data.
And if there are no labels?
That's unsupervised learning. You give the model unlabeled data, and it has to find hidden patterns or structures all on its own. Often it does this by clustering similar data points together, finding natural groupings. And the final step is classification and decision-making. The trained model takes new input, classifies it based on what it learned, or makes a prediction. And that prediction can trigger an action flagging potential fraud, routing a support ticket, maybe helping with a medical diagnosis.
That's a really clear breakdown.
Yeah.
And what's striking is how much the methods themselves have evolved, right? We didn't always have these complex neural networks.
Oh, absolutely. We started with statistical pattern recognition using probability and statistics, things like naive Bayes or support vector machines. Think early spam filters, maybe some medical diagnostic tools, good for structured data.
Okay.
Then there was structural, or sometimes called syntactic, pattern recognition. That was better for complex patterns, where the relationships between components were key, representing patterns as strings or graphs, useful for things like handwriting recognition or analyzing biological sequences.
Right. The structure matters more.
Exactly. But the real game changer, the big paradigm shift, has definitely been neural networks.
Inspired by the brain, right.
Inspired by the brain, yes, and particularly deep learning, which uses many layers of these networks. What really made them such a leap forward, it's this concept of automatic feature learning.
Ah, so the AI figures out the important features itself.
Precisely. In the past, AI engineers would spend ages carefully handcrafting the features the system should look for. With deep learning, the machine itself discovers the most useful, most salient patterns directly from the raw data.
Wow.
It shifts the burden, from human engineering to algorithmic discovery. That's why deep learning is now state-of-the-art for messy, unstructured data like images, audio, text. It learns what matters without us telling it explicitly.
Which brings us deeper into these neural networks, the engines of modern pattern recognition. What is it about their architecture, their structure, that makes them so powerful?
Well, at their core, they're built from these simple processing units, artificial neurons arranged in layers. Each neuron gets inputs, does a fairly simple calculation, and spits out an output. These neurons are linked by connections, often called edges, and each connection has a weight.
A weight.
Yeah, a numerical value that basically dials up or down the strength of the signal passing between neurons. And the whole learning process is essentially about fine-tuning these weights.
Adjusting the connections.
Exactly. And crucially, these networks have one or more hidden layers sandwiched between the input layer, where raw data goes in, and the output layer, where the final result comes out. Having multiple hidden layers is what makes a network deep.
Got it. Deep means multiple layers.
Right. And another critical piece inside each neuron is the activation function. It's a nonlinear math function applied to the weighted sum of the inputs. Without these nonlinearities, even a very deep network would just behave like a simple linear model.
Right.
It couldn't grasp the complex, twisty relationships you find in real-world data.
Okay, so the nonlinearity is key for complexity.
Absolutely.
So the learning process itself, it's really about finding the best set of those weights, right? How do these networks actually train themselves? How do they figure out the right weights?
It's framed as an optimization problem, basically. The network usually starts with random weights, just guesses. Then it iteratively adjusts them, bit by bit, to minimize the error, the difference between its predictions and the actual correct answers.
Oh.
That error is measured by something called a cost function or loss function. And the main algorithm used for this iterative adjustment, this tweaking, is gradient descent.
Gradient descent, I've heard that term.
Yeah, you can picture the cost function as this complex, multidimensional landscape, like mountains and valleys. Gradient descent is like taking small steps downhill on that landscape, always moving in the direction that reduces the error the most, trying to find the lowest valley, the minimum error.
Okay, finding the bottom of the error valley.
Exactly. And the algorithm that really unlocked the training of deep networks, networks with many layers, is called backpropagation.
Backpropagation.
It's a really clever and efficient way to figure out how much each individual weight, way back in the network, contributed to the final error. It does this by propagating that error signal backward through the network, layer by layer. These calculated gradients, the slopes, tell gradient descent exactly how to update each weight to improve the overall performance.
Wow, that's quite an elegant system for self-correction, isn't it? Propagating error backwards to adjust everything.
It really is. It's what makes training these incredibly complex models feasible.
And this ties back to that idea you mentioned, automatic feature learning. How does this whole process actually lead to the network learning meaningful features on its own?
Well, that's arguably deep learning's biggest advantage. Instead of humans defining, say, look for corners or look for texture, the deep network learns a whole hierarchy of features. It starts simple and builds up complexity.
How does that work in practice?
Take convolutional neural networks, or CNNs. They're specialized for grid-like data, especially images.
Right, used a lot in computer vision.
Exactly. Their initial layers might learn to detect very basic things, edges, simple color gradients. Then the next layers combine those simple features into slightly more complex patterns, maybe textures or simple shapes. Subsequent layers combine those patterns into parts of objects, like a wheel or an eye. And the final layers can then recognize the entire object, like a car or a face.
So it builds up understanding layer by layer.
Precisely. This hierarchical structure is incredibly powerful. And then you have other architectures, like recurrent neural networks, RNNs. They're designed for sequential data, things that unfold over time, like text or speech or time series data.
Like understanding a sentence.
Exactly. RNNs have these loops in their connections that allow information to persist, creating a kind of internal memory. This lets them process the current input, say, a word in a sentence, based on the inputs that came before it. That's vital for understanding context and language or spotting patterns over time.
It's really impressive how they build up this complex understanding, but it also leads straight back to that black box problem you hinted at earlier, doesn't it?
It does.
If the machine is learning features we didn't design, how do we know what it's actually basing its decisions on? What is it seeing?
That's the crux of it. The features learned by those intermediate hidden layers in deep networks. They're often mathematical constructs optimized purely for the machine's task. They don't necessarily correspond neatly to human understandable concepts or semantics.
So its understanding could be totally alien to us.
It can be fundamentally different, yes, and potentially more efficient for the task because it doesn't have to stick to our familiar categories at every intermediate step. But yeah, it means we don't always have an intuitive grasp of why it reached a particular conclusion. Powerful, but opaque.
Right. And speaking of the real world, it's messy, isn't it? It's uncertain, probabilistic. Things aren't always clear-cut, yes or no.
Absolutely not.
So while these deep networks are amazing at finding correlations, why do we also need probabilistic models in AI? What do they add?
They add the ability to handle that inherent uncertainty. Think about trying to predict the weather or diagnose a disease. There's always an element of chance, of randomness involved. Probabilistic models are designed from the ground up to capture and, importantly, quantify that uncertainty.
So instead of just saying cat or dog.
Right. Instead of giving you just one single definitive answer, a probabilistic model gives you a probability distribution over all the possible outcomes. It might say, I'm 90% sure it's a cat, 8% sure it's a dog, and 2% it's something else. It's a much more nuanced and, frankly, realistic assessment of the situation.
That makes a lot of sense. What are the practical advantages, then, of an AI that can express that level of confidence or lack thereof?
Oh, several big ones. First, confidence quantification, just like you said. They give you a mathematically solid measure of how sure they are. Second, this enables principled abstention.
Meaning it knows when not to guess.
Exactly. You can design these models so that if their confidence falls below a certain threshold, they simply say, I don't know, rather than making a potentially dangerous low-confidence guess. Think about medical diagnosis or self-driving cars. That's critical.
Absolutely.
And third, robust integration. Because they output probabilities, these models fit much more naturally into larger multi-stage systems. Uncertainty can be properly tracked and propagated through the system, preventing errors from piling up and compounding.
And this area, dealing with uncertainty, brings us to something called probabilistic graphical models, or PGMs, which sound like they help visualize this stuff.
That's a great way to think about it. PGMs essentially merge graph theory nodes and edges with probability theory. The nodes in the graph represent random variables, things we're uncertain about. And the edges between them represent conditional independence relationships, how knowing something about one variable affects our belief about another.
Okay, so the picture itself tells a story about the probabilities.
It does. And the type of graph you use, whether the edges have arrows or not, reflects a really fundamental assumption about the system you're modeling.
How so?
Well, if you use directed graphs, often called Bayesian networks, the arrows indicate directionality. They typically represent causal influences or conditional dependencies. A causes B, or B depends on A.
Like diseases causing symptoms.
Exactly. That's a classic example. The structure of a Bayesian network allows you to factorize the joint probability of everything happening into simpler conditional probabilities based on a variable's parents in the graph. Choosing this structure implies you believe there's an underlying generative causal process driving the system.
Okay, cause and effect. What about the other type?
The other main type uses undirected graphs, known as Markov random fields, or MRFs. Here, the edges have no arrows. They just represent symmetric relationships or soft constraints between variables. Think of neighboring pixels in an image influencing each other. It's mutual, not necessarily causal.
So more like correlation or mutual influence.
Precisely. With MRFs, the joint probability factors differently based on interconnected groups of nodes called cliques. Choosing an undirected graph suggests you see the system as governed by these mutual symmetric constraints rather than a directed causal flow. So the very choice of PGM fundamentally shapes how the AI explains a phenomenon. Is it a chain of causes or a web of interconnected influences?
That's fascinating. The model choice reflects a belief about how the world works. Okay, with all that powerful theory under our belts, feature, vectors, backpropagation, probabilistic models, let's pivot. Let's make this concrete with that real-world case study. Urban waste management.
Yes, a perfect example.
This seems like a place where AI is really calculating, as you said, a pattern of human patterns to manage something complex.
It absolutely is. A modern smart waste management system relies on what we can call a sophisticated data ecosystem. It has to synthesize all sorts of different information to really understand how and why municipal solid waste gets generated.
What kind of data are we talking about?
Well, first you have socioeconomic and demographic data, things like population density in different areas, average income levels, household sizes. That gives you a baseline prediction.
Okay, the background context.
Exactly. Then you layer on consumption patterns. Data from retail sales, information about product consumption, packaging trends. This directly links the waste being generated back to what people are buying and using.
Makes sense.
Then comes the really dynamic part, real-time sensor data. We're talking about IoT sensors, often placed in smart bins that are constantly monitoring fill levels. This gives you a very granular, up-to-the-minute picture of how waste is accumulating across the city.
So you know which bins are full now.
Right. And finally, you add contextual data. Things like live traffic conditions, weather forecasts, a big storm might change patterns, even public event schedules, like concerts or festivals that generate temporary waste spikes.
Wow, that's a lot of inputs.
It is. But fusing all this data together allows the AI to move beyond the old way reactive fixed schedule collections to something much smarter, proactive data-driven optimization. It's literally modeling the rhythms of society that create waste.
And once that waste is collected, AI faces another huge task at the recycling facilities, the MRFs, right? The classification challenge, sorting it all out.
Yes, and this is where we see some really impressive automation. AI-powered robotic systems are increasingly taking over the manual sorting jobs, which are often dull, dirty, and dangerous.
How do the robots see the waste?
They use a combination of sensors. High-resolution cameras are common, but also things like hyperspectral imaging and near-infrared sensors, which can reveal information about material composition that's invisible to the human eye. This stream of sensor data feeds into deep learning models, usually CNNs, which analyze it in real time. They identify and classify the different materials zipping by on the conveyor belt: paper, cardboard, different kinds of plastic, glass, metals, organic waste. Then, robotic arms, guided by the AI's classification, physically separate the items.
And they're faster than humans.
Significantly faster and often more accurate. Some of these AI sorting systems can handle up to 160 items per minute. Compare that to a human sorter who might manage 30 to 40 items per minute.
That's a huge difference.
It is. And AI is also crucial for spotting things that are difficult or hazardous for humans to handle, like batteries mixed in with regular recycling, or medical waste, or complex e-waste. Robots can identify valuable metals and electronics by shape, color, material composition.
And what about contamination? That's a big problem in recycling, right? Stuff being in the wrong bin.
A huge problem. AI helps tackle this at multiple points. For instance, you can have cameras mounted on the collection trucks themselves. These can use AI to detect contamination, like seeing a plastic bag tossed into an organics bin right at the point of collection.
So you can link it back to who did it.
Potentially, yes, or at least provide targeted feedback or enforcement. The results we're seeing are significant. Studies have shown AI sorting achieving high accuracy that reduced overall contamination levels in the final sorted materials by nearly 40%.
Wow.
And there was one case study where AI identified over 300 overflowing bins in just 1 month, compared to fewer than 30 spotted by human drivers. This wasn't just about cleaner streets. It actually generated over $18,000 in extra monthly revenue from collection fees for those overflows and created opportunities to upsell larger bin sizes.
That's incredible. It really sounds like AI isn't just managing waste, it's acting like a city-scale metabolic regulator, as the report puts it.
That's a perfect analogy. The system senses inputs consumption, demographics. It monitors its internal state, those bin fill levels. It predicts future states, anticipating waste surges. And then it actuates control dispatching trucks efficiently, sorting materials accurately.
Sense, predict, act.
Exactly. And that fundamental sense, predict, act loop powered by AI pattern recognition is highly generalizable. You can imagine applying the same underlying principles to manage a city's energy grid, its water supply, traffic flow, maybe even coordinating public health responses during an outbreak. It really points towards a future of more data-driven, intelligently managed urban environments.
So looking beyond just prediction and sorting, how is AI enabling the bigger vision of a circular economy? The idea of eliminating waste altogether and keeping materials circulating.
AI is critical there too. One major area is intelligent logistics. We touched on this, but traditional waste collection routes are usually fixed and very inefficient. Trucks drive the same route whether bins are full or empty.
Right. Seems wasteful in itself.
It is. AI changes that completely with dynamic route optimization. By pulling in that real-time data from smart bins, GPS locations of the trucks, live traffic updates, even weather forecasts, AI algorithms calculate the most efficient collection routes, constantly adapting them on the fly. Collection becomes truly need-based.
And the benefits are?
Pretty substantial. Big reductions in operational costs, fuel, maintenance, driver time, lower carbon emissions from the trucks driving fewer miles, less wear and tear on the vehicles. It just makes the whole collection process much leaner and greener.
That dynamic routing is definitely a game changer. But what about the recycling process itself? Getting more value out of the waste. You mentioned waste valorization.
Right. This is where AI gets into the really cutting-edge stuff. Waste valorization is about transforming waste materials into products with higher value than they had before. Moving beyond just downcycling, like turning mixed plastic into park benches towards true upcycling, creating new materials, chemicals, or energy.
How does AI help with that?
It's often used for process optimization. Many valorization techniques involve complex chemical or biological processes, think anaerobic digestion to produce biogas from organic waste. AI algorithms can monitor these processes in real time and continuously adjust parameters like temperature, pressure, or nutrient feeds to maximize the yield of the desired product, like methane for energy.
So fine-tuning these complex reactions.
Exactly. And even more exciting, perhaps, is AI's role in enabling advanced chemical and molecular recycling. Technologies like pyrolysis or depolymerization can break down really difficult waste streams, like mixed plastics that are hard to sort mechanically, into their fundamental molecular building blocks.
Like taking plastic back to oil.
Sort of, or even back to the original monomers. AI helps optimize these complex chemical processes. And the crucial part is, these resulting molecules can often be used as feedstock to create new plastics or chemicals that are essentially virgin quality. This offers a path to a truly circular economy for materials like plastics, which have been notoriously difficult to recycle effectively.
And AI's role extends even further back, doesn't it, to designing materials in the first place?
Yes, absolutely. In AI-driven material science, generative AI models can now predict and simulate the properties of potentially millions of new polymer structures or catalyst materials vastly faster than researchers could ever synthesize and test them in a lab.
So designing for recyclability from the start.
Precisely. It enables what's called inverse design. You tell the AI the properties you want may be durable, lightweight, and easily recyclable via a specific chemical process. The AI can then work backward to generate novel molecular structures that are predicted to have those properties. It might use techniques like genetic algorithms, for instance, to explore the vast chemical space and find polymers optimized for something like ring-opening polymerization, which is known to be better for chemical recycling.
This sounds amazing, but is it actually being implemented? Are there global examples showing this works?
Oh, definitely. The Global Implementations and Performance Analysis section of the report highlights several compelling cases. In Japan, one sustainability organization used AI-powered image recognition for waste sorting and achieved 90% accuracy, cut sorting time by 70%, and reduced operational costs by 40%.
Huge improvements.
Huge. In Italy, a company called Alia Servizi Ambientali Spa is using AI right now to transform their waste management, specifically focusing on improving the quality and recovery rate of glass waste.
Okay.
Greenopolis in Japan implemented an AI system called Clean Cycle that optimized collection routes and improved sorting. Their results: a 50% cut in operational costs, a 35% jump in recycling rates, and a 45% decrease in the amount of waste ultimately sent to landfills.
Wow, hitting multiple targets there.
Exactly. And Copenhagen, as part of its well-known Smart City initiative, integrated AI and IoT into its waste systems, leading to a 22% increase in recycling rates and an 18% reduction in landfill waste.
So the evidence seems clear. AI isn't just tweaking the old system.
No, it's fundamentally changing the equation. It's helping redefine waste as a valuable resource. This enables concepts like urban mining, extracting valuable materials from our waste streams, and chemical upcycling. Ultimately, this could significantly reduce our reliance on extracting virgin materials from the earth and help create more resilient, self-sufficient local economies.
That is a truly powerful shift in perspective.
Hmm.
Okay, let's pivot again to one of the really thorny issues in AI today.
Mm.
If these models are getting so powerful, so capable,
Mm.
why is it often so hard to understand how they reach their conclusions? We're back to the black box problem.
It's a major challenge.
As these models, especially the deep learning ones, get more and more complex, their internal workings, their decision-making processes become incredibly opaque, right? Almost impossible for us to follow.
That's generally true, yes.
And that opacity, it creates real risks, doesn't it? It makes it harder to debug them when they go wrong, harder to spot hidden biases that might be lurking in the data or the model itself. And fundamentally, it undermines trust, especially when AI is used in high-stakes areas like medicine or finance or the legal system.
You've hit on exactly why explainable AI, or XAI, has become such a critical field of research and development.
XAI, explainable AI.
Right. XAI is all about creating processes and methods that allow us humans to understand, interpret, and ultimately trust the outputs of AI systems. The goal is to move away from black boxes toward glass box models, systems that can, in some way, explain themselves, describe their likely impact, characterize their accuracy and fairness, trace back the reasons for a specific decision.
So how do we make a black box more transparent? What are the techniques?
There are quite a few approaches, but two prominent ones, especially because they can often be applied even if you don't know the model's internal details or model agnostic, are LIME and SHAPE.
LIME and SHAPE, okay.
LIME stands for Local Interpretable Model Agnostic Explanations. The key word there is local. LIME works by explaining one specific prediction at a time. It does this by testing how small changes to the input affect the output right around that specific prediction. It then builds a simpler, interpretable model, like a linear regression that approximates the complex black box model's behavior just in that local region.
So it gives a simplified reason for that specific decision.
Exactly. It might say something like, this loan application was denied primarily because the applicant's debt-to-income ratio was high, and secondarily because their credit score was slightly below the threshold. It gives a local, human, understandable reason.
Okay, that makes sense. And SHAP?
SHAP stands for Shapley Additive Explanations. This one has really interesting roots in cooperative game theory. It treats the input features like income, credit score, etc. as players in a game where the goal is to produce the model's prediction. SHA then calculates the fair contribution of each player, each feature, to that final prediction outcome. It uses a concept called the Shapley value, which is a mathematically sound way to distribute the credit or blame.
So it tells you how much each factor pushed the decision one way or the other.
Yeah, precisely. And SHA values have nice properties. They're consistent and additive. They can be used to explain individual predictions like LIME, but you can also aggregate them to get global insights into which features are most important for the model overall.
So these XAI tools are kind of like translators.
Yeah.
Bridging the gap between the AI's mathematical reasoning and our human need for narratives and causal explanations.
That's a great way to put it. They are translators across a cognitive divide. They help build trust and accountability. But there's an important caveat here. As these AI models get extremely complex, the true, complete explanation for their behavior might actually be computationally irreducible. Meaning, you simply can't compress the full explanation down into a simple, human understandable narrative without losing critical details or accuracy. The explanation might be as complex as the model itself.
So we might never get a perfect, simple explanation for the most powerful AIs.
It's possible. We might have to cultivate a different kind of trust. One based less on complete mechanistic understanding and more on rigorous testing, empirical validation, and proven reliability over time. We trust airplanes without understanding every detail of their aerodynamics, right? It might become something similar.
That's a fascinating point. And this whole challenge also relates to an emerging approach called neurosymbolic AI, doesn't it? Trying to bridge that gap differently.
Yes, neurosymbolic AI is a very exciting area. It explicitly tries to combine the strengths of the two main traditions in AI. It uses neural networks for their powerful pattern recognition abilities, the stuff they do well with raw perceptual data.
The seeing part.
The seeing or hearing part, yes. And it combines that with the strengths of classical symbolic AI, which is good at structured reasoning, logic, planning things closer to human cognition or abstract thought.
So perception plus reasoning.
That's the goal. To create systems that are more flexible, more generalizable, and potentially more inherently explainable, because they would have both this intuitive pattern-finding ability and a capacity for more transparent step-by-step reasoning, trying to get the best of both worlds.
Which leads us, I think, to the biggest, most profound question of all. We've seen how AI can find patterns in waste, in finance, in medicine. Can this unprecedented ability to detect subtle patterns in huge data sets actually serve as a new kind of epistemological tool, a fundamentally new way of generating knowledge about the world?
This is a huge question.
Could AI, as the report puts it, eventually provide the highest level of explanation for humans that need an explanation on all aspects of the explanation of everything there is in existence? Could it explain everything?
Well, it's certainly acting like a powerful new lens on reality, or maybe a mirror to existence, as some sources phrase it. It's recognizing patterns across an incredible, almost unbelievable range of domains.
Give us some examples.
Okay, finance and economics. AI models, especially deep learning ones like LSTMs, analyze market data, news feeds, financial reports to spot chart patterns, predict stock movements, forecast economic trends. It's already deeply embedded there.
Right.
Medicine and biology. We talk about personalized medicine, sifting genetic data for disease risks. But think about DeepMind's AlphaFold, a landmark achievement. It solved the protein folding problem by recognizing incredibly complex patterns linking amino acid sequences to the 3D structure of proteins. The implications for understanding life and designing new drugs are just immense.
Absolutely revolutionary.
Absolutely. Cosmology and astronomy. AI is indispensable now for processing the petabytes of data coming from sky surveys. It classifies galaxies, stars, nebulae, far faster than humans could. And it excels at anomaly detection, finding things that don't fit the known patterns, flagging potentially new phenomena like weird asteroid orbits or unusual supernovae.
Wow.
Urban planning, as we saw with waste, AI analyzes traffic, energy use, population movements to design more efficient, sustainable cities. Generative AI can even create realistic visualizations of proposed developments to help citizens understand and engage with planning decisions.
And even the arts and humanities.
Even there, AI tools are being used for things like vocabulary fingerprinting or linguistic pattern recognition to analyze writing styles, potentially attribute anonymous texts, or study language evolution. In music, AI analyzes vast amounts of compositions to learn patterns of melody, harmony, rhythm. It can classify music by genre or emotional content and even compose novel pieces that sound convincingly human-created.
It's just staggering. The sheer breadth of application. What does it mean that the same fundamental AI techniques work across genomics, cosmology, music, finance, waste?
That is perhaps the most profound implication. It strongly suggests that all these wildly different phenomena, from the folding of proteins to the clustering of galaxies to the composition of symphonies to the generation of trash, must share some deep underlying structural property.
Which is?
They all generate data that contains learnable, predictive patterns. AI is essentially a universal pattern extractor.
So this brings up a huge philosophical question, doesn't it? Is finding these correlations, these patterns, the same thing as understanding?
That's the multi-trillion-dollar question, perhaps? For a human scientist, traditionally, understanding implies knowing the underlying causal mechanisms. Why does X cause Y?
Right, the why.
For an AI, particularly these deep learning models, understanding is primarily demonstrated through predictive accuracy. It learns an incredibly complex mathematical function that maps inputs to outputs very effectively. But that function itself doesn't inherently contain a causal story, a why, in the human sense. It's capturing correlations, sometimes incredibly subtle and complex ones, but correlations nonetheless.
So AI is brilliant at the what and the what next, but not necessarily the why.
That's a good way to frame the current state of affairs, generally speaking, which leads to these deeper philosophical horizons, thinking about AI in relation to concepts like creativity or even consciousness.
Can AI be truly creative?
Well, if you define creativity simply as producing something novel, surprising, and valuable, AI is starting to tick those boxes. It can learn patterns from vast data sets of human creations, art, music, text, and then generate new works that are statistically similar, often plausibly human-like, sometimes genuinely surprising. Some call this statistical creativity. It's pattern recognition and generation taken to a new level.
Okay. And consciousness. That seems like a huge leap.
It is. We need to be careful here. Philosophers often distinguish the hard problem of consciousness, subjective experience, what it feels like to be something, qualia, from the soft problem, the functional aspects like self-awareness, attention, reportability. Current AI almost certainly lacks phenomenal consciousness, the hard problem kind.
Right.
But some argue that advanced AI, maybe large language models during coherent interaction, might exhibit fleeting functional aspects of the soft problem, generating a temporary cognitive model of self, maintaining focus. It's highly speculative, but the conversation is happening. It's not about feeling, but about functional parallels.
Fascinating. So bringing it back to this idea of an AI explanation of everything, what would that actually look like, and what would its limits be?
An AI-powered explanation of everything would likely be a monumental achievement of universal pattern recognition. Imagine a vast, intricate model capturing the statistical regularities of the entire cosmos, from quantum fluctuations up to galactic structures, maybe even predicting societal trends. Incredibly powerful for prediction and control. But it would likely be an explanation built almost entirely on correlation, not necessarily on causation, purpose, or meaning in the way humans typically seek them. It would be the ultimate map of what happens and what is likely to happen next derived from pattern analysis. It wouldn't inherently answer the why questions that drive so much of human philosophy and science. Why is there something rather than nothing? What is the purpose?
So the ultimate AI explanation might be alien, written in math.
It could be a comprehensive description of all the patterns of existence, written in the language of high-dimensional mathematics and complex algorithms, incredibly powerful, potentially predictive beyond our wildest dreams, but perhaps fundamentally descriptive rather than explanatory in the human sense of why.
What an incredible journey we've taken today. Seriously. From the basic algorithms letting AI see patterns, through transforming something like waste management, all the way to these huge questions about AI as a tool for understanding existence itself.
It really covers a vast landscape.
And maybe the final thought for you listening is this. AI is giving us this amazing, unprecedented map of what is, the patterns of reality laid bare. But it's written in this language of correlation, which is both incredibly powerful and maybe a bit alienating. So the challenge for us, perhaps, is how do we reconcile humanity's deep-seated search for meaning, for purpose, the why, with this profound correlation-based understanding that the intelligence we've created is starting to provide?
That reconciliation, that new compact between human consciousness seeking meaning and machine intelligence revealing patterns, it really does feel like it will define our path forward, doesn't it? It's a whole new chapter.
This is DigitView.